Right, so we gave you a code, and the question is discuss the design style. So I need to tell us what is the design style used here, and even if you don't understand what the code does, you should know which design style is used from the statements, of course, that are being used in the code. So can you tell us or tell me what is the design style used in this code and why?
Behavioral.
Why do you think it's behavioral?
Because it contains a process.
Okay, so this is good. I mean, your answer is 50% correct. Yes. So we have behavioral. There is a process, and inside the process we have an if statement, which is a sequential statement. So we have sequential statement and we have a process. Is that it? Do we have any other thing in this code? There's something here, right? Outside the process. What is this? O is equal O underscore. What is this statement? What is the type of the statement? This is the simplest statement. Yeah, in VHDL. Yeah, go ahead, please.
It's maybe it's port map or
This is not port map. Port map, you should see port map in the word. And if when you it cannot be port map because there is no declaration for a component. Port map works with components, so we need to declare components. So what is this statement? What is this? If I write A is equal B, what do we call this statement?
assignment statement.
Huh?
It's assign A to B.
Yeah, we are assigning B to A, but yeah. So what is this type of assignment? It's an assignment, yeah. So what do you call it? It has targets equal expression. What does this mean? What is the statement? A target equal an expression. The expression could be just a simple signal. It could be an input, could be an expression. You need to revise your topics. Yeah, I think it's very bad. This is a simple signal assignment, which we use in data flow, and we use it a lot. So this is a simple signal assignment, and this is a process. So this is mixed. This is mixed design style. We are using two different types of statement. It is mixed because we are using behavioral here and we are using data flow. And by the way, this VHDL code is for a component called the flip-flop, which is a component used in sequential circuits. We will do it later on, of course. For now, you don't need to understand how does it work, because the question is just ask you what is the design style. The next section or next sessions, inshallah, you will know exactly what does this code do. Right. Now, when the statements inside the process are executed, which is basically this if statement, when this if statement will be executed? This is the next question. Can you answer the question?
The if statements will start if the condition is met.
No, before checking the condition. If statement starts from here, it starts by checking the condition.
Yes.
But how does it start? You are asking me when the condition is true or false, this is what will happen. This is part of the if statement. But when the if statement will be executed. Checking if the condition is true or false is part of the execution of the if statement. But when this starts?
When the starts?
When the process starts. When does the process start?
When it gets values for CLK, reset, and EN.
Yeah, it's good. Your answer is almost, you are almost there, but I mean, we need to be more precise. We say that the process will wait. Nothing will happen until there's an event on one of those signals. What we mean by an event is one of them changes value. So it changes from 0 to 1 or from 1 to 0. So otherwise, if let's say this CLK and reset and EN are 0 and they stay like that for 1 hour, the if statement will not be executed. The process will be waiting until one of them changes, or 2 or 3 of them. Any change on those signals will trigger the process. And then this means that the process then will go inside and execute all the statements. Here we have only one if statement. If we have more, all of them will be executed and then back to wait. And I explained this already, yeah, in the lecture. So back to wait, and then it waits until there is a new event. So this is how this works. And then if you remember, last time we told you this process, okay, the statement here will be executed sequentially. This is why we call them sequential statement. So we start first line, next line, third line, and so on until we finish. But the process as a block, I can have two processes in my, let's say I have another process, or I have here a simple signal assignment. This is concurrent. So the process as a whole can be considered as a concurrent statement. It will run in parallel with the other one. So this means that this statement here, the simple signal assignment, it will not wait until we finish the process. It is already in execution in parallel. So it's like that. We have the simple signal assignment and we have the process. So they are like two independent parts running in parallel. Whenever there is an update on this O signal, O will be updated regardless of the process, if it's running or not, if it's waiting or it is in execution. And this is the next question. So this is what we said, discuss in details what happens if we move the statement, this one, the last one, the one that we have here, the last statement, to the beginning of the code. So basically changing the order. So the answer is nothing will happen because they are running in parallel. So you can start with whatever you want. Is this clear? So having this, it's like if you have two simple signal assignments, it doesn't matter with which one you start, because they will run in parallel. Same, if I have a process, the process as a block is considered as parallel with other statements outside the process. Is this clear? And we talk about this in the lecture as well, yeah? So this could be simple signal assignments, could be another process. You can have 2-3 processes in one code. And all of them will run in parallel. So it doesn't matter with which process you start, it doesn't matter with which statement you start. But inside the process, it's important which statement goes first, because it will be executed sequentially. Right. Next question. This one I will not do it. I will leave it for you because we did very similar example. I think if we ask you what is the design, write this. Use a suitable design style. This is a combinatorial circuit, so you need to use data flow design style. And data flow, I think it's easy. You can write this in one statement. D is equal A XOR B and C, or you can have a signal, and then you can do this signal is equal A XOR B, and then you do D is equal C and this signal. So if I call this signal X, I can do X is equal A XOR B, and then I can do D is equal, I'm answering the question anyway, X and B, X and C. Again, those are two simple signal assignments. It doesn't matter with which one I start. I can start with D or I can start with X. It doesn't matter. And this is what I was saying here in the previous question. Is this clear? This is for part B. Right, question 2. We have as well a combinatorial circuit here. We ask you to use the data flow design style. So here we have more than we have a multiplexer, we have an AND gate, and we have a NOT gate. The code for the multiplexer, we did it, and you have it in your lecture. So you have 50% of the answer. But this is a 2-to-1 multiplexer, right? This is a 2-to-1 multiplexer. Now, if I switch to the lecture, just for you to refresh, this is the code for the 4-to-1 multiplexer. For the 2-to-1 multiplexer, what will be the answer? So if I have this one, so we have S. If I call it S, I call this I1, I call this I2, and this I will call it O. So how can I write this code? The same to implement 2-to-1. You have the answer here in front of your eyes. So can you just tell me what should I do? So O is equal what?
I1
I1, good.
when S equals in brackets when S equals the 1 or 0, 0. Yeah, 0.
0 for I1. It doesn't matter. You can start with the other one if you want to put I2, which is fine. But it will be executing. Else
I2
when
S
S
equals
is equal 1, and that's
S
it. Else we put 0, the default one. That's it. This is the 2-to-1 multiplexer. Good, excellent. But now for our case, we don't have I1 and I2. We have, so this I1 comes from, I think, an AND gate, right? If I remember well, let me open this in my computer. So we have, yes, we have an AND gate. So this comes from an AND gate. We have, we call this in1, and we call this in2. And then this I2 as well, it came from, so how can we change this? Now, if I have just this AND gate, so which means O is not equal I1, right? It's equals what?
I1 and I in I2.
That's good, excellent. So I can just remove this, and then I will just, here I can have just, this is an expression. If you go to the syntax of this conditional signal assignment, we say O is equal an expression. And remember, expression, it could be just one signal, it could be just one input. You put is equal B or whatever, like we did here is equal in1, we did here is equal it, or it could be an expression. So here you can put an expression which includes inputs and operator. So it's in1 and in2 between parentheses, and then when S is equal 1. And we'll do the same for the other one. So we'll have an inverter here. The inverter as well comes from here. So which means instead of using I2, I can just remove this and just use here not in 2. And that's it. And this is the code for this circuit. So if I switch to the solution, so you can see the full solution. You can as well work with signals if you want. So this is the solution. This is what I was talking about. So this is the circuit. I put it here as well for you to see. So we have the expression here. So is equal in1 and in2 when select is 0, else not in2 when select is equal 1. And that's it. Of course, I think I'm not talking about the entity. I assume you know how to work with the entity. Yeah, we have in1, in2 as inputs, and we have S select as well as input. I called it here select. You can use S if you want, and that's it. Now you can work with signals. So for example, if you declare this as a signal, you can declare this as a signal. So if I call this X and this is 1, we need to declare them here. Signal X, Y, STD logic. And then I will just take this from here. I can just put X here and just take this from here. I put Y here. And of course, outside the statement. So I will have this conditional statement, and then I will have 2 extra ones where I need to do what is X is in1 and in2. And I need to do Y is equal not in2. So both solutions are fine, are correct. So you can work with the signals, or you can, if you don't want to work with signals, you do the solution as we put it. So this is the solution with signals. It doesn't matter with which statement you start. So here we have three statements. We have this one and this. So those are simple signal assignment, and this one is conditional signal assignment. And all of those are all concurrent signal assignment. They run in parallel. So it doesn't matter with which one you start. Is this clear? So you have both solutions here in the solution, which I will post after the lecture, inshallah. Right. Is this clear or not? And it's the right time to ask questions, yeah?
It's clear, doctor, for me.
Okay, that's good. Right, next question, question 3. I think this one is very simple. So we just say, we ask you what happens if we change the order. Again, we already answered this question, I think 2 or 3 times by now. Those are simple signal assignments, so it doesn't matter which one goes first. Yeah, so this is for the question A, sorry. Oh, sorry, here we ask the design style. Design style is data flow, right? Because those are simple signal assignment. So it's data flow. So this is the first question. And the second question, what happens if we change the order? Again, nothing happens because they are concurrent statements. So I think we did this many times. Now, next question. Now we want to use, we have a big circuit here. And as you can see, it includes 10 XOR gates. And this is a very good example for the use of components. So we have 10 XOR gates and we have 8 what we call full adders, FA. Those are components as well. We gave you the expression for, this is the full adder. It includes 3 inputs, single lines, and 2 outputs. And then we gave you the expressions. This is what is sum, and this is what is cout. So it has 2 outputs. This component has 3 inputs, 2 outputs. Again, and I did this in purpose, we will have the next topic that we will have is about others and comparators. I did this in purpose here, knowing that you don't know what is a full adder, you don't know what is, how does, others work. Even if you don't know how does the circuit work, you should be able to do the VHDL code. If we give you these expressions, and then the question is just to connect the components. Because when you connect components, you just work with the signals and just see how they are connected. So even if you don't know how does the circuit work, you should be able to solve this problem without any issue. Right, so we gave you, so this is the full adder here that we have 8 of them. It has 2 outputs. So this is one output, this is second output. So all of them, they have 2 outputs. Right, and this is how they are connected inside. So these components are used inside this, what we call 8-bit Other Subtractor. So basically, what does this circuit do? It just takes 2 numbers, X and Y, which are both 8 bits, and it will, and then we have this line here. So if this is 0, we will get the result of an addition. If this is 1, we will get the result of subtraction, and that's it. This is, in general, this is how the circuit works. And then we have this. Later on, once we do the other subtractors, if we ask you to design such circuit, you should be able to do it, and you do it from scratch. I think there is a design that we need to do in the lab related to this, but of course after covering the topic about others and comparators. So right, so but again, you don't have to worry about how does the circuit work. It's just to show the connection. So this is the aim of this exercise and how to use the structural design style. Right. So the first question, we ask you to write the VHDL code for this FA, full adder. We call it full adder. And then we ask you to write as well the VHDL code for XOR. So we have FA and we have XOR, and then we use them in structural design style to describe this one. So we need 3 VHDL codes. We need one for the FA. This is first component, component 1. We read this component 2, and then we need the VHDL code. So VHDL for this, VHDL for component 1, and then VHDL for the complete circuit. So other subtractor, if I call it this one. So the first question here is to write the code for the XOR gate. I think you know this. The code for XOR gate is very simple. It's easy. And then we ask you as well to write the code for the full adder. So, and I believe this one is very easy as well. So which design style we use here to do the full adder? We gave you S and sum. So in the entity, what do we have? Is this clear what we want to do? So we write VHDL code for XOR gate, we write VHDL code for this full adder, and then we use them as components here. So how can we describe this?
So the full adder,
adder.
I think it's gonna be probably similar to the MUX.
Yes, so what do we do?
So you need to do your entity and then use one. So one of the sum.
We don't need to use one. We give you the expression. We told you what is sum and we told you what is out. So if I ask you implement this circuit, and I tell you, okay, I have this expression, x is equal a and b. Let's do it. If I tell you this is my circuit, a XOR b and c. So I ask you, we have this expression, and I told you to write the code for this one. So how do you start the code?
So it's gonna be just a simple signal assignment.
Yeah. So you have a and b and c are the inputs,
The
and then
inputs.
we just write x is equal a XOR b and c, and that's it. Right?
Yes.
This is how you. No, we gave you this. We gave you a component that has 2 inputs, 2 outputs, and 3 inputs, and we gave you the expressions. So why do you need to do else? And so how do we implement this one? We gave you the expressions.
So you just have to do your entity, and then inside the entity you put the expressions.
Inside the entity. We don't put
Like
expressions inside the entity.
inside the architecture. The entity you put, you define the inputs and the outputs.
Yeah, in the entity we have I1, I2, C in, and then we have sum and C out as outputs. That's it. So this is the entity for this component, right? And then we go to the architecture, and the architecture, what do we have?
We have sum and count.
Yeah, excellent. This is very simple circuit. I don't know why you are confused. And so we have some. So if I will draw it for you, right? I will do. So we say I will just use the gates. This is I1, I2, C in, and this is sum output. So this is my circuit, is like that. And then I will have I1 and I2, and then we have I1 XOR I2. So we'll take I1 as well, XOR I2. So we'll take them from here, and I will take this from here. And then we do an OR. I'm just following the expression. So we did this, and then we have this, and then we do an OR, and then we do an AND with C in. We finish with an AND for C in. And this is my circuit, C out. So this is my circuit. Oh, sorry. I have two outputs. One is sum and one is say out, and that's it. We just ask you to write the code for this one. This is clearly a combinatorial circuit, and we just write it as you said in the architecture. So the last student who answered, so we just write sum is equal. So I'll switch to so you can see the solution, the code. Right, this one. So this is the first one for XOR. I think XOR is very simple. It's just one statement. And then this is the full adder. So we have in1, in2, cin as inputs. We have sum, cout as output, and I'm just putting them here, following the expressions. Sum is equal in1 XOR in2 XOR cin, and then cout. I'm just writing the expression as it is. That's it. Two lines. One line for each output, because those are combinatorial circuits. Of course, you can use internal signals if you want, knowing that this is the knowing the internal structure of the circuit, because you know it from the expressions that we gave you, this one. So you can always work with signals if you want, but there is no need. You can just do it in one statement. Is this clear? So now we wrote the two codes. So this is for XOR, and this code is for full adder. Now we want to use them as components. So we will use 10 copies of XOR, and we will use 8 copies of full adder in our big circuit by just following the connections as given in the figure. And that's it. You will see that we have many signals that we need. How many port mappings do we need to do in total? So I need to declare two components, one XOR and one FA, and then I need to do port mappings, right? How many port mappings I need in total? So the keyword port map, I need to see it how many times?
Times?
On the signals.
Times?
2 times. Port mapping. No.
I think it's a number of instances you will use, so 18.
It's 18. For each one, I need a port map. For each instance, or for each copy, I need a port map, right? So I need to start with the first full adder, or let's start, if we start with the XOR gate. Sorry. So we start with the first one, and then we move to the next one, the third one, and for each one, I need to show the inputs A and B for this XOR gate is connected to what? And I need to do the same for the output. And then once I'm done with the XOR gates, I can move to the full adder. So good. We need 18 because we have 18 instances in total. We have 10 and 8, 18 in total. So I need to move now. And as you can see here, we have plenty of internal signals that we can use. So I'm going just to use the block diagram that I gave you, and I will just follow it. So as I told you, any line inside the circuit connecting two components can be declared as a signal. So if I take this first XOR gate, so the first input of the XOR gate is connected to what? A.
Zero.
So we have 0. It's just grounded. So this is 0. And by the way, for the port mapping, you can put 0 if you want as a value. So 0. Or you can put 1. You can do this inside the. So this is connected to 0. And the other one is connected to what?
The long line, so sub, I think.
Sub is this one. Sub is this line here. So this sub is an input in our circuit, and is connected, as you can see, to all XOR gates. So one input of the XOR gate is sub. So in the port mapping for all XOR gates, we should see sub, right? And then we have 0. And then what else? The output now. We have 3, right? Input, 2 inputs, and 1 output. So the output is connected to this line. So I need to declare it as an internal signal, XOR 1. So I call it XOR 1, just to know that it's coming from XOR, first XOR gate. And then I did XOR 2. I followed this naming. I mean, you can choose any name you want. So you can put it X1, X2, X3, X4, and so on. And then, as you can see here, we have as well lines here. This is the output from the full adders going to the, as an input to the next full adder. So it's called C1, which is the carry. So the full adder, as we said, we have, if I put it here again, full adder has 3 inputs, 2 outputs. So we have sum and we have carry out. Input. So this goes to an input of the next full adder, and so on. So we keep doing this. Anyway, you just follow the circuit. Yes.
Doctor, I don't understand the port map. Here in this example, how can I define it?
Port map.
Yes.
We did several examples in the lecture. So
Yeah, I know the concept, but in this example, I don't understand how we find it.
okay. So we take, if I take the first case, this one, the XOR gate, right?
Okay.
I need to do port map for this one. I need to do for this. I need to do for this, and so on. I need to do for all of them. When I do the port map,
I need to do for FA or no?
of course, we need to do for FA. We need to do. I ask you this question: how many port maps do we need to do? And one of the students, he answered 18, which is the correct answer. So I need to do 10 port maps. I mean, if I give you the I give you the FA and I give you the XOR gate, you need to connect them. If I ask you to do this circuit on breadboard, you need to connect them, right? You need to take the OR gates are not the XOR gates are not connected, and the FAs are not connected. You put them on the breadboard and you start using the wires and to connect them. So you start with, if I start with this XOR gate, I know it has 2 inputs, and this is what we did in the, it has 2 inputs, A and B, and it has an output C, right? This is the XOR gate.
Okay.
Right. When we do the port map, we need to look into the inputs and the outputs, how they are connected, to what signals or to what inputs or outputs are connected to. So if I take this one, this is A. Let me reduce the size of. Let's try. Yeah. So this is A, this is B, and this is C. So A is connected to what?
0.
0. So when I do port map, I will write port map and then 0. B is connected to what?
Sub.
Sub. I mean, the student who was asking the question, I prefer to hear his answers. So B is connected to sub. Do you see it here, right?
Yes.
So sub is an input in my circuit. Sub is one of the inputs of my circuit. And then C is connected to what? C is connected to this line. It's connected to this line. I need to define it because this is a signal, a wire. It's not an input, it's not an output. We don't have it in the entity, so we need to declare it. I called it XOR 1. When I do the port map for this full adder, first full adder, I need to use XOR 1 as well because it's used here as a signal. Is this clear? Now if I do the port map for this full adder, Of course, we need to repeat all what we did here for all gates, XOR gate. So I need to move to the next XOR gate. Let's do the next XOR gates and then we do the full adder. So XOR gate 2, this one. So I need to do port map, same. So the inputs of this XOR gate is connected to what?
SUP.
So A is connected to sub, good. And then
Y0.
Y0, and Y0 is the first line of this Y. Y is a bus. So we need to declare X as a bus, Y as a bus. So we need to have the entity first, yeah, for this big circuit, and then we go to the port mapping. So Y, and you remember I showed you last time in the lecture in an example. If I want to use the first line of a bus, I can just use Y0. If I want to use second line, I'll just use Y1, and so on. So Y0, the first line of this bus, is connected to the inputs B of the second gate. So you're right. So it's Y0. And then the output is another signal here. So it's another line, which I need to declare as a signal. So I call it XOR 2. And that's it. So I will do the same. I will go to the next one, 3. And I will repeat this. So for 3, it will be again sub. And then it's Y1, right? And then XOR 3. I need to do this for all gates, and that's it. Once I'm done, I can switch to the, you don't have to start with the XOR gates. You can start with the FA if you want. You can do one XOR gate, one FA, one XOR gate, doesn't matter which one you start with. Now, if I go to the full adder, so FA, port map, let's take the first one. So the full adder has I1 as input, has I2 as input, it has C in as an input, and then it has C out and sum as output. So I need to see 5 ports, right? Because it has 3 inputs and 2 outputs. And this is the code for the, so it has 3 inputs and 2 outputs. When I do the port mapping, I need to consider all of them. So first 3 inputs and then the next 2 outputs. And now I'm going to do the port mapping. So I1 is connected to what?
X0.
X0, good, excellent. So I can put X0 here. I2 is connected to what?
XR2.
XOR 2, which comes from the previous XOR gate, XOR 2, right? That's good. And then Cin is connected to what? To XOR 1. I'll just complete my, and then Cout is connected to C1. Now, which one goes first, sum or Cout? This depends what do you put first in the entity. So you need to follow the order. And then sum is connected to Z0. I'll just put Z0 is the output, is a bus. It's an output. And that's it. This is all what I need to do. So you work with signals and you just connect your components. You have the full code here. So basically, of course, we need to start with the entity. We have X and Y are the buses, 7-bit, 8-bit, sorry, and then we have sub, and then we have Z as a 7-bit, and then we have C as an output. I'm just using this one, this figure here, to guess the inputs and the outputs of my big circuit. This is for the entity. And this figure here, it shows me the details, how it's done inside, how it's connected. So first I need to as a component, so this is all. So copy paste, remember we have the code, right? We wrote the code for XOR gates, copy paste. And then I go to the next one, FA, full add, again, copy paste. So here do you see we put sum first and then C out. So we need to be careful when we do the port mapping. We should consider sum first. So sum is connected to what, and then C out. If you swap them, you will get it wrong. Your circuit will never work. And then, as you see here in red, I put a good number of signals. So those I declare them all as signals, and in my code, those are all signals that we have in red in the figure. And then that's it. I will just do the port mapping. Here in my solution, I started with full. So those are 8 full adders, and these are 10 XOR gates. You can start with the XOR gates and then do the full adders. It doesn't matter. You can mix. You can do for one XOR gate, one full adder, one XOR gate, and so on. And that's it. I put this here as an example, so for each one. But I in
Doctor,
yes.
this circuit, it's better to do it by the flow design.
No, this one is better with the with this one. This is the first one. With data flow, you need to write 2 expressions. So you need to write one expression for all XOR gates. Each one will have one. And then for the full adder, you need 2 expressions for the 2 outputs. Right? So basically, we'll keep repeating what we write here twice. Those 2 lines, you need to have them for all the full adders. So you will have more lines in your code compared to this solution. So this is the best one.
Yep.
Yes, you can do it if you want. I'm not saying
Okay.
you cannot. You can do it, but this is the best. You asked me about the best solution. This is the best. Yes, you can always work with just, as you said, the data flow, but you will need more lines in your code. So we have 8, so you need 16 lines just for the full adders. And then you will need another 10 lines for the XOR gates, which is those 10 lines, for example. I have just 10 lines as well. So this is the best. And again, just following the logic diagram. Each input, I will look for the input is connected to what, and that's it. I will just write the name of the connected input. So we see here, we have sub in all of them, because the sub is connected to all XOR gates. Is this clear? Example for the use of components. Even if you don't know how does it work, you solve to write description. Right. I will go to the next question. I don't know if did you start the VHDL in the lab or not yet?
No, not yet.
Okay. So when you start the VHDL, you will see that the board that we will use, it has, do you know what is a 7-segment display?
Yeah, we used the 7-segment displays before.
You used this before, okay. We have 2 types, right? We have common anode and common cathode, 7-segment displays. There is a difference between them. Do you know what is the difference between them?
Yeah, the common anode, it's 1 is off, 0 is on. Common cathode is 0 off, 1 is on.
Yes, good, excellent. So just to summarize, we have 2 types, common anode or common cathode, but one is the opposite of the other. I mean, those 7-segment displays, you can think of them as like, we have 7 LEDs. And to turn one LED on, for common anode, or for common cathode, if you put VCC, you get it on, or you put 1, you get it on, 0, you get it off. For the common cathode is the opposite. Sorry, for the common anode is the opposite. If you want to eliminate or to make 1 on, you need to put 0. Is this clear? So for example, here, if I take this one, this is the FPGA, and we have those segments. So we have, and by the way, those are the segments. So we have A. Let me, we didn't put them here, but this is A, this is B, C, D, E, F, G. So the segments are like that. So now those are 8 lines or 7 lines from the FPGA connected to the 7 segment. So if I want this A to be on, the rest I want them off, I just need to put 0 here. This is common anode. For this board, the board that you have, the 7 segment displays used are common anode, which means they operate with the inverse logic. So if you put 0, you get it on. Now, if I want just segment A to be on, I will just put 0 here and just put 1, 1, 1, 1, 1, 1 here. So all will be off except A. So for example, if I want to display number 3, what do I need to do on those lines? I want to display 3.
A, B, G, C will be 0.
That's good. Excellent. So we need those segments. This is 3. This is how we display 3, right? So we need A, B, C, D, and G. Those are E and F. So E and F should be off and the rest should be on. So which means E and F, we need to put 1. Remember, is the inverse logic. So we need to put 1 here, and the rest are 0. So if I do this, I will get 3 displayed. Okay, so that's good. So this is for the, so this question here, in addition to this, so we will use one of them. There are 4 in this board. We want to use one of them. And we want to use as well 4 switches. There are switches as well on the board. So we want to use 4. So basically what we want to do, once we have those connections, we want the write the code, the HDL code to be run on this FPGA that can be used to display the number given as an input using the first 4 switches. So we have 4 switches on the 7 segment display. Nothing should be displayed when the number is more than 9. Right, so we want to display 0 to 9. And we get them from the switches. So let me explain further here. So we have an FPGA. So this is the FPGA. This FPGA, we have 4 switches connected to it. So if I do the switches this way, so switches could be on or off. So this is 4. Those goes as inputs. Now, switches could be on or off. If I have 0, 0, 0, 0, this means all the switches are off. What are the possible values that I can have from switches? How many possible values?
2, 1, or 0.
No, 4 switches together. Yes, one of them it could be 0 or 1. Now I have 4 switches. So what are the possible values?
8.
16.
No, 16. I have 4. So 4 bits. 2 power 4, 16. I can have those possible values. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, right? 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, and so on. Yeah, I'm not going to put everything. And then 4 zeros, 4 ones, sorry, 4 ones, 4 zeros, and so on. And then 8 zeros, and then 8 ones, and so on. So we have 16 possible possibilities, yeah, with those 4 switches. So what we say, if all switches are off, for example, I will display 0. If we have this combination, I will display 1. This I will display 2. This I will display 3. I will display 4. I will display 5. I will display 6, from the switches. So I'll take the value of the switches. So like I'm taking the binary from the switches, I will display it as decimal in the 7-segment display. 7, and then 8, and then 9. Any value more than 9, I don't want to display anything. So I want all switches to be off. Oh, sorry, all 7 segments to be off. I don't want to display anything. So here I have the 7-segment display. Again, I need 7 lines. So if I put them this way, so we have A, B, C, D, and those are connected to 1, 2, 3, 4, 5, 6, 7. Yeah, so those are connected to the 7-segment display. This is what we want to do. So we ask you to write the VHDL code to be able to do this. So here we have A, B, C, D, E, F, G. Right. We need to describe the circuit here that will take the value of the switches and then output the right combination to eliminate the number that we want to see. Is this clear? So now we start. Yes, go ahead.
Sorry. So, Doctor, here we will eliminate 8, 9, and we take only the 7 until 7, from 0 to 7.
No, from 0 to 9. And then anything after 9, because we will have as well 10, 11, 12, 13, 14, 15, right? I don't want to display this. This I want it off. But for those 0 to 9, I want to display them.
Okay.
But the rest after 9, I don't want to display. I just want to keep the 7-segment off. Right. So I think we need to start first with the entity, right? In the entity, what are the inputs and outputs that we have?
You have the 4 inputs from the switch.
Excellent. Good.
Then 1 output, which is a bus.
Good. Even for the switches, I can have it as a bus. So you can have separate lines, or you can have it as a bus. So we can have entity, begin, the name, and then is, and then we do port, and then, as you said, we have 4 lines. So I can call it SW. Input. This is input, right? STD, logic, vector. Three down to 0. And then we have 7-segment, if I call it SSD, 7-segment display, out, STD logic, 7 down to 0, and that's it. And that's it for the entity. I have just one input, which is a bus, and 1 output. And then I need to start my code. So basically, I think, and this one is very simple. So I need to check what is SW. So based on the value of SW, I need to eliminate this. So I need to find the combinations here. So if SW is equal 0, if this is the combination that I'm getting from the switches, what should be the output? SSD. I need to consider all those cases, right? So if SW is equal 0, 0, 0, 0, this means all switches are off. What should be SSD?
0, 0, 0, 0, 0, 0, 1.
We need to turn, yes, you are right. So we need to turn, remember, yeah. So this is the 7-segment. Put it big here so you can see. So this is A, B, C, D, E, F, G. So I need all segments to be on except G, right? G is the last one, so I need all of them to be 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, except the last one. So SSD should have this value, right?
But please, why again the G should be 1, not 0?
I want to display 0. To display 0 on the 7 segment, which segment should be on?
Yes, the all except G.
Yeah, all except G, yeah. So if, and remember we said this 7 segment display is common anode. So which means if I want one to be on, I need to put 0. If I want one segment to be off, I need to put 1. I want G to be off, so this is why I need to put 1. So A, B, C, D, E, F, G.
Doctor,
Right?
why are they reversed? Why is it not A, B, C, D, E, F, G?
Sorry?
Why is it not A, B, C, D, E, F, G? Why is it G, F, E, D, C, B, A?
We start with the first one here. The first bit is A, B. This is how how they are connected.
Oh, okay, so it's reversed.
It's up to you. I mean, if you take an external 7 segment display, you can connect it the way you want. But here for this FPGA, they are connected like that: A, B, C, D. So the first bit is the first one, is A.
Oh, thank you.
So it depends on the connections. But of course, if we give you an external 7 segment display and we ask you use it, you can do the connection that you want. It doesn't matter which one you start first. Okay. So I need to do the same, all this for all possibilities here: to display 1, to display 2, to display 3, to display 4, 5, 6, 7, 8, 9. And then anything more than 9, we don't need to display anything, which means we want all of them to be 1, 1, 1, 1 off, all of them off, right? So more than 9, SSD should be equal to this. I hope it's clear. It's not complicated. It's very simple. So once you understand the logic, what we want to do.
Just one more question though.
Yes.
For the 7 segment display, it's reversed, but the actual the switch, for the switch, it's not reversed, yeah?
It's not really. You have this first one is connected to the first bit, the first line, and so on.
I understand. No, I mean like for the when we write the expression for the switch, the assignment for the switch, is it gonna be 0, 0, 0, 0, then 0, 0, 0, 1, or we have to also make it 1, 0, 0, 0?
I don't know if I'm getting your point, but this is switch 1, this is switch 2, this is switch 3, this is switch 4. So yeah, is this clear? So switch 1, switch 2, switch 3, switch 4.
Okay, now I get it.
And that's it. So we will work with it as it is. So basically, this is what I did here. In the solution, you will see I started with this table first. So basically, we need to find the combinations to display. This is what I was explaining. So if I want to display 0, digit 0, I need to do 0, 0, 0, 0, 0, 1. If I need to display 1, I need to do 1, 0, 0, 1, 1, 1, 1, until I finish all 9 possible combinations, and then others. For the rest, there should be 1, 1, 1, which means all off. If the question was with a common anode or common cathode, we'll just inverse the zeros and ones here, and that's it. And now we need to go to the code. And I'm going to use one simple signal assignment. Oh, sorry, one selected signal assignment. Here the switch, I call this BCD, yeah? and then SSD call it segment 7. So those are my two inputs. Now I'm going to use this in my code by just doing with BCD select. I can do it with conditional signal assignment as well. So you can do segment 7 is equal this value when BCD is equal 0, 0, 0, else, and you can keep repeating this. Or you can do it with selected signal assignment. So here basically I'm just using this table. So this the output segment 7 should be this when this BCD is equal 0, 0, 0. And then it should be equal to this next one when the switches are equal 1, 0, 0, 0. And then until I finish all of them until 9. Once I'm done, I will just do this one when others. The good thing we have others here in this statement. So when others, we want them all off. Yes.
Here he does not use the process.
I don't need a process. This is a combinatorial circuit.
So he used which design?
Data flow. This is selected signal assignment. This is the select signal assignment. The same that we used for the multiplexer. Do you remember this one? So here, this is conditional. I can solve it with conditional if I want. And we have the selected, this one. We solved the multiplexer with the selected, and we solved it with the conditional. Is this clear? I can do the same. I can solve this with the condition. I can solve this with the conditional. I just write it in the right, syntax, and that's it. This is one statement. This is basically one selected signal assignment, and that's it. This one, all from here to here is one statement. You can do exactly the same thing with conditional. If you want to use process, you can use, for example, the switch statement. But again, it's not the best solution. No? So I can use a process if I want to do it with a process. And then in the sensitivity list, what should I put? So the process should be executed each time. What the change comes from where?
Comes from switch.
Switch is excellent. So we just put BCD here. Remember, BCD is the switches, yeah, in our example. So I just put BCD here, and then begin. You can do it with a process if you want, but again, I think the other ones are simple. So which statement do you think? You can do it with if statements if you want. If, else, if, else, if, else, if, right? You have, so the condition is on BCD. If BCD is equal 0, 0, 0, then segment is equal this value. Else, if BCD is equal 0, 0, 0, 1, then, so you can do it this way. You can use as well the case statement.
So here,
case. So you can write something similar to this. Yes.
So here, the best solution using data flow.
It's data flow. This is a combinatorial circuit. And to be more precise, this is called the decoder. So for each code here, we have a different output. And I put a lecture on decoders for you to work on it on your own. Yeah, this is what I do every year. I always give one simple topic to students to read it on their own. It's very simple. Decoder is very simple. This is a decoder. So basically what we did here is a decoder. We guess the BCD, the switches, we decode it, and we have one output for each combination. That it's just, I think, few slides, 10 slides for this topic, and we showed you even some examples. So this is the best design style. for it. You can solve it if you use a process, it will work, it's fine. And again, you can work with if BCD is equal 0, 0, 0, 0, then put segment, if I call it SSD, is equal, and then you put the value 1, 0, 0, the one that we need in the table first. Else, if, and you put all your cases, and then you finish with one else with no condition for this, the last one. You can do it with case statement. So there are different solutions. This one we can do it with selected, we can do it with conditional. That's it for this topic.